Hello and welcome back. In the past couple of videos, we looked at how pseudo-inverse works and how it helps to unmix patterns and get us the uh, correct target output. Now, what we are going to do is uh, take this one step further, and I'm thinking this of a magic. So I promise you won't be disappointed by the end of this video. Let's imagine we have uh, input which are three images. So this is one image, this second image, this is the third image, and each image we see that it has a letter, so A, B, C. And what we are going to do is whichever pixels we have these shaded, those would have a value of 1, as you see here. So this pixel is shaded, and so we have value of 1 right here, and the pixels that are not shaded, so like this one, it has a value of -1. And so we have this 5 by 5 matrix, if you will. And then what we are going to do is uh, uh, this would be our matrix, this would be our input P. So this is our input P, but in the in the previous videos we saw that it was a vector. So what we will do is, let's call this P1, call this P2, call this P3, and we'll flatten these out into a single column. So those three could then be put in to get our uh, matrix P, as we see here. So uh, this, when we flatten it, it would become a vector. So and that would just become one column in this matrix P. And this is, it's hard to do this manually, so taking the inverse of this. So for the first time in this video, I'm going to use code without doing the manual calculations, and it just makes it so much easier. uh, let's see what we have then. Here is the we are doing it this in Python. So I've imported NumPy and Matplotlib, and then this is the input P1, the array that I talked about right here. So they say, so what I've done is, in addition to this 5 by 5, I've gone ahead and added a border to this. So we have this blank row, square around it, which is all minus ones. So these minus ones right here, right here, and right here. And so that just gets us a good feel to see that character A, B, and C. This is RB, which is P2. This is the C, which is the P3. And I'm just plotting this here so you can see the A, B, and C. These are the images we have. And for each of these to be identified, we also define a target. So for P1, we say that this is the output signal. If that's the output, then it is A, where I've put 1 in the first position. For target B, target 2, to identify it as the letter B, this has 1 in position 2, and likewise for target 3, for C, we have this 1 in the position 3, and we combine these to create our matrix T as for target. Now for creating the matrix P, we take each of these vectors P1, P2, P3, flatten it using the ravel, and then put them in an array and then transpose it. So what we get is a matrix that has 49 rows and 3 columns. And why 49? Because we have this 7 by 7 pixel image for each alphabet. And just to check if the column in the matrix P that we just created represents the alphabet which we said it would be, what I'm doing here is just pulling the first column from the matrix P, reshaping it back to 7 by 7 and trying to plot it, and it is the same alphabet A, which is a 7 by 7 pixel image. Awesome. So, and here we can see that the shape is 49. So 49 by 1 that we would be using. Now, the very first step, as you probably already know and have seen this multiple times now, is we'll calculate the weight by calculating the dot product of target with the input matrix transpose of that. So I'm going to use np.matmul t comma p transpose, and that gets us this matrix. That's the weight matrix which we have using the Hebbian rule. We have calculated, so easy, right, with the code. Then we use that weight matrix W, denoted here by W heb, and to calculate the target. So we'll use the same P1, P2, P3 as test vectors to see what target we get, because it will be just easier to compare with the values that we have. So if we now try to uh, 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 take the T have and uh, do the dot product of W with P transpose, we get a uh, prediction uh, that we see here, which is completely different than what we have for the target. In target for A, which is the T1, we should have gotten 100, but we have a completely different set of values. Likewise for uh, T2, we should have gotten 010, but we get completely different values. And for T3, we should have gotten 001, but we have completely different set of values here. And that's where the pseudo inverse magic comes in. What we know that to calculate pseudo inverse, we do this P transpose dot P and then dot that with the P transpose again, and we use that P transpose matrix to then uh, calculate the new weights. So this block is simply calculating that uh, P inverse matrix. As you can see, I've done it manually. We could have also have done this directly using the np.linearalgebra.pinv, and it'll give you the same output. This is just to sort of check what we tried to learn in the past few videos does work here. And the P inverse matrix has the shape 3 by 49, as you would expect, the same shape as the weight matrix W. If you remember, uh, the input P matrix has a shape 49 by 3, that's R by Q, and then the weight matrix has the shape S by R, in this case that is 3 by 49. So yeah, S by R as in number of inputs, so acid Q, so we could say that would be S, and that's how we are going to dot this. Now once we calculate this weight matrix, which is uh, dot product of T with P inverse rather than a dot product of uh, T with just the P. We are using P inverse here, and that gets us uh, uh, that gets us uh, uh, the weight matrix. And now when we try to use that weight matrix to calculate the targets, here is where the magic happens. And now if I try to dot the W inverse, the weight matrix that has the pseudo inverse used in it with the input P1, we get 100. That's identical to T1. This minus 0, uh, we can think of it as same as plus 0. So this does match the target that we had. Then same thing for T2, it does match the B target 010, and same thing for uh, T3, which is for C, and it does match 001. Well, by now, if you are not impressed, I would be, I agree with you, because here is something that will start showing the magic of pseudo inverse. Here, what I've done is the bottom half of the images, I've deleted them. As you can see, we just see the top part of A, B, and C. Now, what we'll do is we'll use these half images along with the pseudo inverse weight matrix that we have calculated, uh, uh, or to say it correctly, the weight matrix that we calculated using pseudo inverse of P. And if we do that dot product, we see that we are able to correctly identify that this first image is A. As you see, this matches with the target T1. Likewise, this matches with the target T2, which is B. And that means that just by having this upper part of B, we were able to identify that that image belongs to the uh, uh, class B or the target T2. And again, just knowing this upper half of C, we were able to correctly identify that that is letter C. And as you can see here, this is 001, and that is same as the T3 target that we have for C. And if that is not magical enough, let's go on one step further. Here is the same image ABC, where we are now going to add some noise, and this is where we create a noise using we use Gaussian noise, and we create 7 by 7 matrix uh, using np.random.randn, and then just multiply it with some value to play around with how much noise we want to add, and then just add that noise to each of these images. So I create a copy, reshape it, add the noise, and then plot it below. As you can see, if the noise is 0.5, we can we can still see the image. So if you want to go a bit slower, let's say if the noise is zero point 0.1, we see that the noise is there, but then it's pretty clear that we see it's ABC. And now if we try and predict with the uh, P weight matrix that we calculate using pseudo inverse, we see that we do get correct predictions of 100 for A, that's T1, 010 for B, that's T2, 001 for T3. And that's you say, well, that is not impressive because the signal is pretty clean. I already see that it's A, B, and C. Why don't you go ahead and add some more noise? So let's try and increase the noise to, let's say, increase the threshold to 0.5. Now there is plenty of noise, and we can see that here. If we go ahead and try to predict, this is the magic. We can still correctly predict that the uh, P1, this first image with the noise, is referring to A, this is referring to B, and this is referring to C. How amazing is that? Now, if we keep going, I'm going to increase the noise further. Let's say we go all the way up to 1. Now, rather than zero point 0.1, which is 1. And as you can see now, it's barely, uh, the letters are barely visible. I mean, I cannot make out if which one is A, B, or C. Well, now we can, because I know that this left one is A, middle one is B, and the rightmost image is C. But just looking at it, it's not immediately clear which one is which. But if we take that image, flatten it, and dot it with the weight matrix that we created using a pseudo inverse, look what happens. We get a correct prediction, and this tells us that that first image is class T, so that is A because it matches with the target output for T1, and this second one is, if we run this again, you can see that this is 0 1 0, this is 0 0 1, and so this tells that the second image is B, the third image is C. And we could go further until it crashes. So let's try to bump it up further to 2, and now uh, it's extremely difficult to see which letter is which. And so if we still run this through the weight matrix, it's amazing that we can still correctly classify each of those letters. So the first input, it correctly says that that's the letter A, because we get 100 that matches the target output T1 that we have. This matches T2, this matches 33, so this is for B and this is for C. Awesome. I think as long as uh, uh, these noise can be separated, uh, we can detect the signal, and that is extremely powerful. If you ask me, if to identify signals based on so much noise. But if I go keep going further, say if I go to some value higher, let's say 3, then this will crash. And as you can see now, uh, we were still able to, so this didn't work, this doesn't work, and this, so there is a lot of interference or overlap, and that's where this won't work. But it's pretty impressive that having so much noise in the image, we can still use uh, these simple linear algebra methods to create some magic, to find patterns in noise. And next, I'll try to explain why that magic happens. Let's say that the matrix of stored patterns is P, which is this one, as we just said, that is equal to P1, P2, P3, all the way up to PQ. And so the size of this is R by Q. Now, if we have a test vector x that belongs to the space to that space R, then and this could be our single noisy image. So that could be our single noisy image that we just saw. Then we can compute the coefficients. So C, which is the coefficients, is equal to P plus that's x. And as we already know, this is P plus, which is equal to the we have this transpose dotted with P, inverse of that dotted with P transpose. And what this tells us is how much of that x is similar to the stored patterns. And then we can do the reconstruction, which we can denote here by x cap, which is equal to P C, or that is equal to P plus x. And so we can then calculate the residual between this and this, or the error. So we can say that the residual R, or the error, is equal to x minus x cap, and that is equal to I minus P plus x. So here x is the component of so uh, x cap is the component of x that lies inside the span of the stored patterns, and this is the signal we want to keep. And R, which is this one, is the component of x that is orthogonal to that span. So the orthogonal to that span, which is the error, that is something we associate with noise, that gets thrown away. And so we only need P, that is the stored patterns, and a single vector x to compute both x cap and r. Now if we look at an example, let's say we have two input vectors, and let's say these are orthogonal to each other. So we have p1 which is equal to 1 0 0. We have p2 which is 0 1 0, and we can use these to create our matrix P, which we said would be something like this. And so we can put them as columns right here, and that's our matrix P. Then because this is orthogonal case, we can say that this P plus is equal to P transpose. And now let's say we have a test input, a noise input, which looks like 0 0.9, 0 0.2, 0 and then a large value of 5.0. So this is noisy, as we can see. We can find the coefficients now using this. So we can say that C is equal to P plus dotted with X, that is going to be P transpose dotted with X, that is equal to, I'm directly going to write the values, that's 0 0.9, 0 0.2. And if we now reconstruct X cap from this, that is going to be equal to PC is equal to 0 0.9, 0 0.2, 0. And if we now calculate the residual R, which is the difference between X and X cap, that gives us a vector which is 0 0 5.0. And as you can see, this error or uh, noise component is orthogonal to the entire pattern plane, so it becomes the residual, so this part, and gets removed. And so we didn't need other noisy samples, just the patterns plus the signal to or to match it with the stored patterns. And next we look at an example where we have inputs that are not orthogonal. In this case, we use the same P1, but we'll change the P2. So P1, say P1 is still 1 0 0. P2, we'll change that to 1 1 0. And now our input matrix P is going to look like this: 1 0 0, 1 1 0. And here, if we compute P transpose P, that will get us 1 1 1 2. I've already done this, so I'll write it directly here. And then if we compute the inverse of that, P transpose P, inverse of that, this would be 2 1 minus 1 minus 1. And if we again use the same noisy vector as input, or we could use this, let's use a different one. We use a different one because I see that I have used a different one in my example. So let's use X is equal to 1.1, 0 0.9, 5.0. So note that this noise is the same level here. And if we now try to compute the dot products, first we'll calculate the pseudo inverse, which is P transpose P inverse dotted with P transpose. That is going to give us 2 minus 1 minus 1 1, and then here we have 1 0 0 1 1 0, and that gives us a value of 1 minus 1 0 0 1 0. And we can then compute the coefficients C, that is equal to P plus dotted with X. And so we have our pseudo inverse matrix right here. We dot that with X. In this case we have 1.1, 0 0.9, 5.0, and that gets us this would be 1.1 minus 0 0.9 and 0 0.9. So we have 0.2 and 0.9. We can then use these to do the reconstruction to get x cap, which is p not with c, and so the p we already know it's 100, 110, and the c we just now calculated 0.2, 0.9. That gets us value of 1.1, 0.9, and 0. So we can now calculate the residual r, that is x minus x cap, which is going to be equal to uh, if we look at the x that we have, it's that, so these two cancel out, so we have 0 and then we have 5.0 right now in here. So as you can see, just as in the previous case, the large z noise, which is this one, is removed, and uh, here we can also see how the p transpose, unmixed, or the overlapping contributions. So the coefficients in C correctly identify the combinations of P1 and P2. So in the end, uh, if we look at the decomposition in linear algebra, the let me write that down. X is equal to P plus X, and the uh, this is the part that matches subspace in the subspace, and then this is the error part, I minus p plus x, and this is what is orthogonal to that subspace, which is the residual part. And so we compute the two terms directly from p and x in this case. So again, the magnitude of r, uh, the magnitude of the residual tells us how noisy or how out of space the vector is. So I hope with this video you got another good intuition about the Hebb's neural network, where it fails, how pseudo inverse can help rescue that, and I also have some tangible examples which you can try and plug in different inputs that you like, helps you identify uh, the real pattern, even if there is a lot of noise present in it, because uh, noise sort of gets separated out as orthogonal component in the process, as we just saw. If you have any questions, comments, or suggestions, please do let me know in the comment section below. I hope to see you all in the next video. Please like, share, and subscribe. It helps me stay motivated to create more content like this for you all. Thank you. Bye for now.